In this section, we're going to spend a little bit of time looking at two particular kinds of truth sets that come up very often. So as we saw in the last section, if we have a proposition over a universe, then its truth set is the elements of the universe for which the proposition is true. And there are two cases that we think about and that often crop up in maths. The first is whether the truth set is empty or not. And the second that we often think about is whether the truth set might in fact be the entire universe. And these crop up so often that we have special notation for them, and that's what this lecture is all about. So the first one that we're going to have a look at is called the Existential Quantifier. If Pn is a proposition over some universe, and its truth set is not empty, so there's definitely at least one element of the universe for which our proposition is true, then we say mathematically there exists an n in U such that Pn is true. You don't always have to put the is true in. Since this is quite a lot of writing, we abbreviate this using symbols. So this backwards E over here is read as there exists. So we have there exists an n, and then we use the shorthand that we've put there exists an n in brackets and a little subscript for the universe that we're talking about. So there exists an n in our universe, and then we don't say anything about such that, that's just implied, and then we write Pn. And that means that Pn is true. So we've abbreviated this whole long sentence into that short little snippet of symbols. If it's clear which universe we're talking about, then we just omit the subscript U. So let's have a look at a couple of examples. If we look at this statement over here, this is read, there exists a k in integers such that k squared minus k minus 12 equals 0 is true. And really this is just another way of saying that we can find an integer which solves the equation k squared minus k minus 12 equals 0. In fact, there are two integers that solve it, but that doesn't matter. This statement is still true. There is at least one. So whenever we're saying there exist, we mean there is at least one. We can also say, if we're thinking about integers, there exists a k element of integers such that 3k equals 102, which is true. However, if you replace 102 with 100, this statement would be false. There are no k's for which this is true. In order to say that there isn't a single k for which a statement is true, we will often put a line through that there exists. So here's another example. We make the statement there exists an x in real numbers such that x squared plus 1 equals 0. Now this is false, so if we want to write a statement that is true, we say there does not exist an x in real numbers such that x squared plus 1 is equal to 0. The next quantifier that we're going to look at is called the universal quantifier. Now, when we looked at the existential quantifier, that meant that there was at least one element for which a statement was true. Now we're looking at kind of the opposite thing, where we're saying we have a proposition over our universe, and our proposition is true for all elements in our universe. So our truth set is the entire universe. And if this is the case, then we say for all n in our universe, our proposition is true. And again, we have symbols that we can abbreviate. This upside down A says for all, or sometimes you'll hear it as for every. And then we use the same idea for all or for every n in U. Proposition Pn is true. And this upside down A is called the universal quantifier. Again, if our context is clear, then we just leave out mentioning which universe we're talking about. So how could we use this universal quantifier? Well, we know that the square of every real number is bigger than 0. So we write that mathematically as saying, for every x in real numbers, if we square it, it's bigger than or equal to 0. Here's another statement that uses the universal quantifier. So this says, for every n in integers, n plus 0 is equal to 0 plus n, which is equal to n. And that's true, and this is called the identity property of 0 for addition. So there are some different types of notation that get used that you might see in different textbooks. So for the universal quantifier and the existential quantifier, we've seen this notation. The notation that I actually prefer is this notation on the third line here, where we make explicit for every n element of un, Pn is true. We could also write that, if we're thinking about the existential quantifier, we could write there exists an n in our universe such that Pn is true. So all of these mean the same thing, and you can pick which works for you. So let's get a little bit of practice. So we're going to let our universe be all animals. And then we're going to let C of x be our proposition that x is cold-blooded, f of x be the proposition x is a fish, and s of x be x lives in the sea. And what we want to translate is every fish is cold-blooded, so we want to write that mathematically. So we start by saying, well, we need every fish, or we need every. So in every, or for all, and now we're thinking, well, we want to say, if you're a fish. So for all x, such that you're a fish, will mean that you're cold-blooded. So let's just take a moment to see if this makes sense. So this reads, for every animal, if you're a fish, then you're cold-blooded. So that makes sense. All right, let's have a look at our second sentence. So now we want to translate this into English. So our first bit says, there exists an animal and then this next bit says, that lives in the sea. And this bit says, is not a fish. So take a moment, pause the video if you need to, and translate part C. So if we want to check this, so our first bit says, for all animals, and the next bit says, if the animal is a fish, then it lives in the sea. Alright, so we've done some not very mathematical examples. Now let's see if we can use quantifiers to state that for every positive integer, there is a larger positive integer. So when we start parsing this idea, we're going to say the first bit we need for every positive integer. So we want to have for every x in the positive integers. And now we want to think about the next bit. We want to say that there exists a larger positive integer. So we want to say that there exists, well, let's call this larger positive integer y. So there exists a y in positive integers such that y is greater than x. So we can start building up sentences that include both universal and existential quantifiers. We'll come back to that in a moment, but we're going to start by thinking about how we negate universal and existential quantifiers. So it turns out that they're actually complements of each other. So let's look at an example. If we take our universe of animals, and we're going to say f of x is the statement x is a fish, w of x is x lives in a water. Now we know it's not always the case that if an animal lives in the water, then it's a fish. In other words, if we made the statement for all animals living in the water means you're a fish, is false. Another way to think about this is, well, then there must be some animal that lives in the water and is not a fish. So if we want to say this is not true, we can say, if it's not the case that for every x living in the water means you're a fish, is the same as saying that there exists an animal who lives in the water and is not a fish. So notice what we've got happening over here is, if it's not the case that things are true for all x, then it means that we must be able to find an x for which one of the situations is not true. So just to have a look at this. So we've already looked at this first case over here. Symbolically, we can negate the for all with a there exists, for which the statement is not true. And if you think about it going the other way around, if you want to say that there does not exist a p for which this is true, then you want to say that for everything in the universe, our statement is not true. So this is how you negate our quantified expressions. So for example, the ancient Greeks discovered that root 2 is an irrational number, i.e. it's not a rational number. So symbolically, we could say it is not the case that there is a number in rational numbers such that r squared is equal to 2. Or you could say that for every element of the rational numbers, r squared is equal to not 2. And they're both saying exactly the same thing. It's just that one uses a negated existential quantifier and the other uses a universal quantifier. And if you do a check over here, this statement says it is not the case that for every n in prime numbers, so this is prime in this case. Usually we've been saying that that symbol means positive numbers, but here it's prime. So this is saying it is not the case that for every prime number, n squared minus n plus 41 is prime. And it turns out that this is equivalent to saying there exists a prime such that n squared minus n plus 41 is composite. And remember, composite means it's not prime. They both say the same thing, and so we can figure out, if we figure out that one is true, then the other one must also be true. If the one is false, then the other is also false. All right, so let's take a little bit of practice working with quantifiers. So here we've got our universe is the universe of all books, and we've got the following propositions. B is the proposition X has a blue cover. M is the proposition X is a mathematics book. U, so be a little bit careful here, U is that the book is published in the United States. And R, notice this is a statement that includes two variables, X and Y, says the bibliography of X, so that's book X, includes book Y. So maybe pause the video and see if you can work through these, and then when you're done, come back and we'll talk through them. All right, so let's translate into words. Well, one starts quite simply. So there exists a book. And now let's have a look. So B of X says it has a blue cover, and we're negating that. So this is saying there exists a book that does not have a blue cover. Okay, moving on to the next one. Now we're saying for every book in our universe, we have M and U. So M is being a mathematics book or published and published in the United States implies that it has a blue cover. All right, so for all books, if the book is blue, if the book is a maths book and published in the US, then it has a blue cover. Okay, so we've translated it. We're not saying that this is necessarily true. All right, let's have a look at C further down here. So now we've got there exists a book in the universe such that it's a mathematics book and it doesn't have a blue cover. All right, and now let's have a look at D. So here we've got, there exists a book such that for all books in the universe, being a maths book, so if it's a maths book, if X is a maths book, then the bibliography of X includes Y. So I'm going to use X and Y when I write this out. So there exists a book Y such that for all books X, if X is a maths book, then the bibliography of book X includes book Y. So once we start having multiple variables in a proposition and you're translating into English, it's helpful to just use the same symbols. So we used X and Y. If you're only talking about a single variable, then you can just talk about the book or a book. But more variables, you start to need to name them. Okay, let's take a moment to go the other direction. So now we want to take an English statement and translate it into mathematics. So here we've got every book. So that's going to be for all books in our universe. Every book with a blue cover is a mathematics book. Now we can rephrase this into the language that we know is for every book, if it has a blue cover, then it's a mathematics book. So this we would rewrite as if it's a mathematics book, then, if it has a blue cover, then it's a mathematics book. So getting a handle on when to translate into an if-then is quite useful. Okay, let's have a look at F. So there are mathematics books that are published outside the United States. So here we're saying that there exists at least one book published outside the US. So we want that there exists a book which is a mathematics book, and it's not published in the US. All right, now we want to say not all books have bibliographies. Now this one takes a little bit of thinking. So we want to say that there is a book that doesn't have a bibliography. So this is where it's useful being able to switch between not all and there exists at least one without. So we want to say there exists a book, and now we want to say it doesn't have a bibliography. Now, a bibliography, we have a statement that R of X means the bibliography of X includes Y. So if we want to say a book doesn't have a bibliography, we want to say that it doesn't include any other books in its bibliography. So we'll say for all books, it is not the case that our bibliography of the book that we're looking at contains any other book. So this might seem a little convoluted and it's worth thinking through, but given the statements that we're using, this is how we would say this. Obviously, if you used different basic propositions, you would have something else. So a couple slides back, we saw an example which used multiple quantifiers. So just to clarify how these work, if you have more than one variable, you can quantify it more than once. And if you're just using, for example, universal quantifiers, it doesn't matter what order they go in. So you can have a look through these examples over here. And the same goes for existential quantifiers. If you've only got existential quantifiers in your proposition, or you've only got universal, then the order really doesn't matter. These examples are pretty good because they combine negation and multiple quantifiers. So let's just have a quick look over here. So if we're taking our proposition to be the proposition over x and y, which says that 2x minus y equals 2 and 4x minus 2y equals 5, now this is always false. And so we could write these in equivalent ways. We're saying it is not the case that we can find an x and a y such that our q is true. We could also swap our orders of y and x. Notice here, now we can say for every y in real numbers, there is not an x that makes this true. Or in fact, we could use for all y, for all x, it is not the case that q is true. And you can swap around your orders of x and y as well. So it turns out there are many, many ways that you can write any particular compound logic statement. However, you need to be a little bit careful. If you have existential and universal quantifiers mixed up, then the order cannot be exchanged without possibly changing the meaning. So let's have an example. So our first proposition is going to be for all a in the positive real numbers, there is a b in the positive real numbers such that ab equals 1. So let's just think about what this is saying. This is saying if I take any positive real number, I can find a b such that ab is equal to 1. And this sounds true. If you take any positive real number, so I don't know, let's take pi, then I can find, so I'm not going to use that symbol, then taking b equal to 1 over pi, which is also a positive real number, means that I can take pi times 1 over pi, and that's equal to 1. So that's definitely true. But now let's see what happens if we switch our order of quantifiers. So now we're saying there exists a b in positive real numbers such that for every a in real numbers, ab is equal to 1. So now what this is saying is that there's some particular b, 1b, which no matter which a I take, when I multiply them together gives me 1, and that's clearly not true. So from this example, you can see quite clearly that order of existential and universal quantifiers is super important. So what I suggest that you do is spend some time working through these examples. And when you're done, you can come back and check the answers, which are below. It's really important that you spend face time with this material, getting it clear in your head in the way that makes sense to you. So here are the answers. And you can also spend some time looking at them. They'll be in the full notes.